One of the conceptually important tests for the convergence of the series is called the limit comparison test. So before we start, let us talk about how we need to apply the test for the convergence of the series. So first of all, we need to get the general term an, and we need to check what is its limit, right? So at some point when n becomes large, it should so the sequence of the series, the terms of the series, should converge to some finite number, right? And let's consider the general case of the series. So n goes from 1 to infinity. It is going to be a1 plus a2 plus and so on plus an plus and so on. So it is important for us that the terms of the series are becoming so small so that we can just neglect them. We can just write them as zeros, right? So in this case, it is really important for us the first m terms, let's say, so that afterwards the terms are becoming zero so that we can just neglect them. So in this case, if the terms of the series at some point just becomes simply zero, in this case we have a chance that the sum of the series becomes some finite number. Otherwise, if it is not zero, for example, if it would be just simply 1, and we would just add a lot of ones, infinitely many ones, and we would just get infinity as a sum, right? So the important condition which we need to check always for the series is that the limit of the general term should be equal to the 0 as we increase the n. So, but at the same time, it doesn't guarantee that the series is going to converge, right? So sometimes, for example, for this series, n goes from 1 to infinity, 1 over n squared. So let me write this as 1 plus 1 over 4 plus 1 over 9 plus and so on. So the terms are becoming faster. So the terms are becoming 0 faster than in this case. So n from 1 to infinity, 1 over n, which can be written as 1 over 2, 1 over 3, and so on. So in both of the cases, at some point, the terms are becoming so small so that we can neglect them. So here as well. So, but the problem is here, the terms are becoming faster, 0, than here. So that is why this sequence, so this series is convergent, and this series is divergent. So it appears it is not just important for us to have the 0 terms on our series at some point, and it is also important at the same time how fast we will get the 0 terms in our series, right? So if we get the 0 terms in our series fastly, then we have a chance that our series becomes a finite series, convergent series. If the terms of the series becomes 0, but really after long time, then the sum of the series, the sum of the terms are already become so large that it is considered as infinity. So the limit comparison test tells us that if we have the one series, if I would like to check for the comparison, so I need to find another series, Bn, which is going to have the similar speed of the convergence of the sequences, right? What does it mean? So for both of the terms, so both of the series, the terms become 0, and for both of the series, the time when the terms of the series become 0 are more or less the same, right? So the limited comparison test tells me that if I would like to test for the comparison of this series, what I need to do is I need to take the ratio of the general forms of the two series, limit when an divided to the bn, when n goes to infinity. If this is some constant, it means that the time when the terms of the series becomes to be equal to the 0 are more or less the same, where c is some positive constant. Then in this case, so if the series Bn is convergent, then the series An is also convergent. Or if the series Bn is divergent, then the series An is also divergent. The logical explanation of this test is in the following. So we're going to consider the t-series so that the terms become zero more or less at the same time, right? So that is why we're taking the ratio. And in this case, if one of the series is convergent, then the other one is also convergent. If one of the series are divergent, then the other one is also divergent. So let us consider an example for the convergence. So we are given this series in the following form: 1 over n squared plus 5. N goes from 1 to infinity. So I'm going to denote the series in a general form as an. It is going to be 1 over n squared plus 5. And I would like to compare this with the another one, which is bn, which is going to be 1 over n squared. So we know that 1 over n squared is a series, is converging series, right? It's convergent. So what I would like to do is I would like to find the real ratios. So the limit of 1 over n squared plus 5 divided to the 1 over n squared, when n goes to infinity, it is going to be the limit of n squared divided to the n squared plus 5, when n goes to infinity, is equal to the 1. So this is some positive constant, and it tells us that the terms of this series and the terms of the series are becoming zero at some point, and they're becoming zero more or less at the same time. So that is why if this series is convergent, then this one is also convergent. So let us consider another example. For example, I would like to test for the convergence of the series Tn minus 1, n goes from 1 to infinity, so Tn minus 1. So I would like to denote this as an, which is going to be 1 over Tn minus 1, and our Bn can be denoted as 1 over Tn. So it is clear that Tn minus 1 is going to be smaller than t in the power of n. If we take the reciprocals, it's going to be 1 over Tn minus 1 is going to be bigger than 1 over Tn, right? So what I want to say that this series is convergent, right? If I take the sum, the series is going to converge. And I don't know, since this one is bigger than this one, it doesn't guarantee that it is going to be convergent as well, right? So just simply pure comparison test doesn't work here. So what we need to do is we need to use the limit comparison test, right? We need to check whether the terms of the series becomes to be equal to the zero more or less at the same time. So in order to do this, we need to find the limit of bn divided to the an, or an divided to the bn, it doesn't matter in this case. So it is going to be the limit of 1 over Tn minus 1 divided to the 1 over Tn. N goes to infinity, and the limit of Tn divided to the Tn minus 1 when n goes to infinity is equal to the 1 again. So it means that the terms of the series becoming zero more or less at the same time. So that is why if this sequence is convergent, then this one is also convergent. So now let us consider an example of the divergent sequence. So we're given this ugly series in this form, n in the power of 4 minus 1 from the square root divided to the n cube. Okay, so I would like to denote the general form of the series in the form n4 minus 1 divided to the n cube. And another series which I would like to compare this with this one is, let's say, n squared divided to the n cube. So which is actually similar to the 1 over n, right? So they have the similar rate of the they have the similar rate to converge to the zero, right? Okay, so now I would like to compare the an with the bn. So n goes to infinity. Let me just divide square root of n4 minus 1 to the n cube to the n squared divided to the n cube, right? So we can just simply cancel n cube and n cube. What is left is limit goes to infinity. So instead of this term divided to the n squared. So let me rewrite the n squared in the power as n in the power of 4 from the square root. And on the numerator, we're going to have n in the power of 4 minus 1, right? So we can write this in a form as a square root of n4 divided to the 4, which is 1 minus 1 over n in the power of 4, right? from the square root, n goes to infinity, and when n goes to infinity, the second term just simply becomes to be equal to 0, and what is left is simply 1, right? So which tells me that this series and this series, they behave more or less in a similar manner. So since we know that this Bn is similar to this one, which is divergent, so that is why Bn is also divergent, so that is why An is also divergent. Actually, we could just show that An is divergent by just comparing An with this harmonic series right immediately, right? So we could just find the limit n goes to infinity of square root of n 4 minus 1 divided to the n cube divided to the 1 over n immediately, right? So I'm just comparing this An not with a Bn, but with this harmonic series. So in this case, we would have the limit of n goes to infinity square root of n 4 minus 1 divided to the n cube divided to the 1 over n. It's going to be simply n square, right? So it would be simply, again, 1. In the same manner, we can write this in this form. It's going to be 1 minus 1 over n 4, where the second term goes to the 0 and n goes to the infinity, and we will have simply 1. So it means that this series can behave like this series, and since this one is divergent, then this one is also divergent.